All right, everybody, let's get started. We are on lecture 17. We're kind of like right where we should be. Today we are going to be discussing some additional stuff related to bolted connections, and we're finally going to do an analysis example. I threw a lot at you yesterday or Wednesday. And ultimately, everything that I threw at you yesterday can actually be summarized in one slide, which I'm going to pull up here in a second. So if I threw a lot of data at you, it's not bad. And the exercising that data is pretty straightforward. We are going to, on Monday, discuss some what I would call additional items to consider in the design side, like how you deal with spliced connections, considering the number of bolts, bolt arrangements, and so on and so forth. And we'll get into design a little bit later. But today I want to get into bolted connection analysis. So actually assessing a connection and determining its capacity, because it's going to follow the same mode as we did with tension members. First, we learned how to assess a connection or assess a member. Here's a member. How much can it hold up? Right? Then we said once we understand that, we will be able to size a member in order to safely resist load, and that's design. And we'll do the same thing with bolted connections, welds, columns, beams, what have you. It'll be the same mode across the board. Now, in terms of class logistics, all the attendance is now up to date, done, good, ready to go. All the outstanding homework, graded. All the solutions outstanding, posted. Boom, done. Except for exam 1, my target on that is Monday. I decided it would be a good idea to give 52 students an Engineering 216 exam on Thursday, so I have a stack on my desk. But yours is first because I gave your exam first. So my goal is to have it graded this weekend, have it done on Monday. Everybody's shaking their head. So
that's just about 216. Yeah, about how many people are. What class were you in?
Corbly 117.
There's only like 15 people that are 216 last semester.
Yeah, I have 52. I had 60.
I had a lot of them.
Some people waited on taking it last semester.
I sure wish I waited. Wait.
No. All right, everybody. So my goal is to have the exam graded and have it back to you on Monday. I will probably give you an emailed grade report similar to how I did instructional analysis because it's a lot easier to just sort of send it out that way. I'll give you your hard copies back when they're graded. Okay. Any questions? All right. I could summarize everything in the last lecture here on this slide. So we talked about introducing bolted connections in our last lecture. And if you remember, I introduced two classes of bolted connections. There is a bearing type connection and a slip critical connection. We're going to deal with slip critical later. But the only difference between a bearing type connection and a slip critical connection is that there is an additional limit state that we need to consider for slip critical. So for bolt bearing, we have these two limit states. For slip critical, we have three limit states, these two and then the third one. And it's pretty easy to deal with as well. For bolt shear capacity, what we have to do is we have to know what type of bolt we're dealing with, what grade I mean, whether it's group A or group B. Remember, group A and group B are not real, like there's no such thing as an actual group A or group B. That's just AISC's means of clumping together bolts that have similar mechanical specifications all into one group for analysis. We need to know the thread condition, whether or not the threads are included or excluded from the shear plane. We need to know how many shear planes we're dealing with, and we need to know the bolt diameter. And after that, it's a lookup. We did an example in class last time where we computed the capacity, whereas we don't really need to do that. We can just look it up. So if you haven't tabbed that, that's a tabbable page for sure. And it's not just that table. There's a couple tables like right around that section of the manual, table 7.2, table 7.3. We may or may not use table 7.2 dependent upon time, but definitely table 7.3 for slip. So they're all really in the same spot. Like I actually have that tabbed on my manual as just a little bolt symbol because there's a lot of stuff there. Now that's bolt shear. With bolt bearing, we kind of have to do a little bit of math with that one because we have to assess the condition of the plate. So because remember, bolt shear is the bolt actually failing, the bolt snapping in half. Bolt bearing is the plate failing as a result of contact between the bolt and the plate. And so we have our capacity is listed as the minimum of 1.2 LC-TFU or 2.4 dB-TFU, and that is the capacity per bolt. Now, what we do in practice, and we're going to have an example that looks at this here in a second, is we're going to look at we're going to look at a connection that has an arrangement of bolts. Now, if you look at this image here on the bottom, I've got green bolts and yellow bolts. The yellow bolts are the bolts on the edge, and then the green bolts are what would be the interior bolts. So when we look at capacity, what we do is we compute the capacity of an edge bolt, we compute the capacity of an interior bolt, and then we just multiply. So we would say that this connection has 4 edge bolts and 16 interior bolts. So we just compute the capacity of each and then add it up. Now, everything in that expression is plug and chug except for what I would call the newest expression, which is LC. LC is the clear distance between plate edges. So we have an LC for edge bolts, or LCE, and an an LC for interior bolts, LCI. And they're pretty easy to derive. Just for the interior bolts, we just take the bolt spacing minus an entire hole diameter, because we go half and half on each end. And then for the edge bolts, for LCE, it's just the edge distance minus half a hole diameter. And the hole diameter, because we are looking at the actual physical dimensions of the plate, and we are looking at the plate in a little bit more of a localized fashion. We're not asking how much of that material transmits load to the rest of the member. We're just looking at the actual plate itself. We add a 1/16 of an inch to the diameter of the hole, not an 1/8 of an inch. Any questions? Now, if you remember with tension members, we had strength limit states, but we also had service limit states. What was our service limit state for tension members? The slenderness limit. It had nothing to do with load, right? It was just ensuring that the member achieved certain geometric properties or fit within certain geometric constraints. And there were reasons for that. The reason for the L over R limit for tension members was so that the member could be, that it met handling limits and whatnot. Whereas for connections, there are similar geometric constraints. Different reasons, but valid ones nonetheless. And so when you're laying out a bolted connection, there are 2 things that you need to consider. You need to consider bolt spacing limitations, and you need to consider edge distance limitations. The gentleman who came in here on Wednesday and talked a lot about, like, it's great to know how to do the math, but there's kind of like a real world aspect to what we're doing. You remember that? These bolt spacing and edge distance limitations really sort of hit at the real world aspects of steel design, and they're really important for maintaining performance in the real world. And you'll understand that here in a second. But the only thing I will say is that these bolt spacing limitations and edge distance limitations do not guarantee bolt bearing capacity. You do still need to compute the capacity of the plate to ensure that it adequately supports the load. These layout requirements are for a different reason altogether. Okay, now let's talk about minimum bolt spacing. Okay, the minimum spacing of a bolt, so this is all in Chapter J. I'm in J3.3, 16.1-130. I've screen clipped it here into the slideshow, but it says that the minimum spacing of a bolt shall be, the spacing of a bolt shall be no less than 2 2/3 times the nominal diameter of the fastener. It also says that there's a preferred spacing of 3 times the diameter. Now let me ask you a question. What do you think happens, or why do you think we have a minimum spacing for a minimum bolt spacing limit? Or let me ask it to you this way. What issues would arise if the bolts got too close together? I'm talking real world. Ignore the math, ignore the equations. I'm not talking about that. Real world. What would happen if the bolts got too close together? What's that?
No material between the holes for strength.
Okay. That's a strength consideration. I'm saying ignore strength. This has nothing to do with strength. That's the answer. The bolts get too close together, you can't actually tighten them. You have to get a wrench around the bolts to be able to tighten the connection together, right? So the bolts have to have some separation so that you can actually put the darn thing together, right? So according to typical structural bolt geometry, if your bolt spacing is at least 2 2/3 times the bolt diameter. So for a 3/4 inch diameter bolt, that means that the minimum bolt spacing is 2 inches. So if your bolts are at least 2 inches apart, then you should be able to tighten them without issues with constructability. Does that make sense? So it has nothing to do with strength. Again, now what you were saying is, you were saying that there needs to be enough material to resist the load. That is true. I'm not saying that it isn't. This is why what I said earlier, I said that just because you meet bolt spacing limits doesn't mean you don't need to check bolt bearing. You still need to do it. They are separate issues altogether. Okay? Yes, sir.
Do we use, whenever we're calculating this, do we use the minimum or the percentage?
That's a great question. I'm glad you asked that. So what I'll say is this, and I'm going to talk a little bit about this later. There are some common practices in the world of steel design that I'll talk about a little later. I will make sure that on homework problems, if you are designing, you will know whether or not I want you to use preferred bolt spacing or minimum bolt spacing. I am not going to make that confusing for you as a student. But if you're assessing a connection to determine whether or not it is in compliance with the specification, use the minimum, right? Because it's either minimum or maximum, and it's got to be in between. So for specification compliance, use the minimum. Does that make sense? Now the second sentence has to do with slotted holes. We're not going to really deal with slotted holes for the purposes of what we're dealing with. The vast majority of bolted connections in most civil engineering structures use standard bolt holes. That doesn't mean to say that slotted holes aren't used. They are, but they usually only have very specific applications. Like, for example, in bridge land, we have fixed bearings and expansion bearings, and the expansion bearings utilize slotted holes to allow translation. And as long as those slotted holes are far enough away from the adjacent element that you can tighten it, then you're good. So, does that make sense? Now, I'm going to flip the script a little bit, and I'm going to ask you about, well, hold on. Let's go to minimum edge distance. I want to talk about maximum bolt spacing here in a second, but let's talk about minimum edge distance. Minimum edge distance is, so what we're talking about with minimum edge distance, I'm going to use this little table here as an example. So bolt spacing is how far apart bolts are from each other. The minimum edge distance would be, okay, here's the table, right? Let's say I drill right here. Minimum edge distance is the distance from the drill bit, where I put the drill bit, to the end of the plate, right? To the center of the hole, to the edge of the plate. And the spec lists this out in a tabular fashion. More often than not, it's whatever the bolt diameter is plus 1/4 of an inch. There are some, what I would call some, tweaks here and there in that, which is why it's listed as a tabular listing. But by and large, that's a good rule of thumb. The reason for a minimum edge distance requirement, this one I'm going to tell you, this has really nothing to do with bolt tightening, as Mr. Narrowway pointed out, but this comes from the fabricators, right? Because what the fabricators are saying is that if I have a plate of steel and I need to drill a hole in that plate, that drill bit needs to be somewhat away from the edge of the plate so that I actually get a good hole from the drilling process. How many of you have ever done any like woodworking and whatnot? You drill a hole too close to the edge of the board, right? The hole doesn't come out right. It doesn't have a good circular geometry. So if you want a good hole, you got to back it in a little bit, right? Y'all know what I'm talking about? It's the same idea here. So the fabricators are basically saying, dependent upon your bolt diameter, you need to back it off a little bit from the edge of the plate so we get a good quality hole at the end of the day. So that's where minimum edge distances are coming from. With me so far? Now, let's talk about maximum bolt spacing and edge distance. So going to what I'm talking about here and what Mr. Narrowway brought up about the bolts knocking together when you're tightening them, what's the issue on the other end? Okay, what if I have bolts that are a foot apart? Well, I'm certainly not going to have an issue tightening them together, right? That's not going to be a problem. I'm going to be very easy to take two bolts and tighten them together. But let's talk about the other end. Why do I have maximum bolt spacing and edge distance requirements? And I think that the answer can be revealed if you think about how the specification is written for this. So take a look at this. So it says the maximum distance from the center of any bolt to the nearest edge shall be 12 times the thickness, but shall not exceed 6 inches. So that's the edge distance requirement. But for the bolt spacing requirement, look at what it's saying. It's saying for painted members, there's a limit. But for unpainted members, there's a different limit. Why? Why would we care about a maximum bolt spacing limit? What are we concerned about? I'm asking. It has nothing to do with load. What do you think? Let me ask it this way. When you take a bolt and stick it through two plates and tighten that bolt, what's happening to the two plates? Smacking together. Now, let's say I have a plate joined by two bolts. So let's say I got a plate and a plate on top of this, and I stick two bolts through it, but those bolts are really far apart. Think there's going to be a little gap between them plates? What would Dr. Waite be worried about getting between them plates? Water. And what does water do to steel? Corrosion. Look at the way the bolt spacing limit is listed. There are two different types of limits dependent upon whether or not you're dealing with painted members or unpainted members not subject to corrosion, or unpainted members which are subject to atmospheric corrosion. So if you look at the numbers, what the spec is saying is that if you got a situation where you're dealing with unpainted steel, or a situation where you're dealing with a component subjected to corrosion, the limits get more stringent. They get more restrictive. Does that make sense? So what we're going to do in this class is, unless otherwise stated, we are always going to assume that we're dealing with either unpainted or weathering steel. Have anybody ever heard of the term weathering steel? Do you know what that means? It's awesome. What is weathering steel? I'm curious. Does anybody know? That's 100% correct, yes. And the way that they do that from a metallurgical standpoint is, I mean, I'm really oversimplifying it. They basically throw a little bit more nickel into the steel mix. That's kind of what they do. But that's oversimplifying it a little bit, but that's kind of the idea. And so it exactly does that. When it's exposed to atmosphere, what it does is it forms a rust patina, right? That rust patina, when it's done, it actually looks like your coat. That's kind of what the color looks like. That has this sort of burgundy maroon color. If you ever see any steel bridges out there that have that sort of burgundy maroon color to it and they don't have any paint, that's what it's for. Now, one of the things that DOHs require, though, is if you ever look at a bridge, where does the drainage happen? On the ends, right? That's why DOHs still say, I want you to paint the ends, because they want that extra layer of rust protection at the ends where the water's going to drain. Does that make sense? See, this is all real world stuff. So. Questions? See, look at me, I'm nice. I put everything all in one little place so you can snapshot or selfie or Instagram that and go, boom, here's all your limits all in one spot. So bolt spacing limitations, we have a minimum or a preferred. The maximum we're going to take is either 14 times the thickness or 7 inches. To be honest, in most typical connections, we never really butt up against the minimum spacing. We always tend to butt up against we don't tend to butt up against the maximum spacing. The minimum is what we tend to butt up against because we want our connections to be sort of small geometrically. The bigger they are, the more plate we need to connect them. Like a bigger connection is just more steel, more money. So we try and keep them kind of compact if we can. The minimum one is the only one that you kind of need to look up. Everything else is computable. And the edge distance requirements, I'm not saying you desperately need to tab that page in the manual, but at a minimum, I would have a tab in the manual for Chapter J, because there's a lot of stuff in Chapter J we will utilize. Okay. Any questions? Let's do a problem. All right. Now we have a bearing type connection that we are going to assess. we're going to determine the design strength for the bearing type connection shown. Now, one of the things that is maybe unclear now, and I am structuring both this problem and your homework assignment so that you don't need to worry about this, but one of the things about bearing and connections in general is that there's always two cases because you're connecting one member to another, right? So when you do bolt bearing calculations, you might need to look at either the plate on the left or the plate on the right. But for this problem, if you look at the connection, they're both half-inch thick plates. Like it's a half-inch thick plate connected to a half-inch thick plate, and all the dimensions are consistent. So that part's pretty easy. And for your homework, I'm only having you check one case. The different cases of bolt bearing is something that we're going to talk about and assess on Monday. I just wanted that to make sense. Now we got A36 steel along with 7/8 inch diameter A325 bolts. The threads are excluded from the shear plane. And we're also going to determine whether or not the connection meets layout requirements. Now, I could also take this member and compute gross section yielding, net section fracture, block shear rupture, all that hullabaloo that we all love, but I'm not going to worry about that today. We've already had that. Y'all know how to do it. We can move on. And let me pull up the notebook. I already have all this on the notebook as well. Okay. I'll give you all a sec to write some of this down. All right. With me so far? Still writing? All right, I'll give you a sec. I'm nice like that. I didn't turn my phone on silent. My apologies there. Yes?
What's the 2 inches to the left and right of the bolt?
That's a great question. That's so let me put that up here to try and clear that up. So this dimension is 3 inches. This dimension is 2 inches. And so this dimension right here is also 2 inches. Does that make sense? So what you're seeing here, see why this is a solid line and this is a dashed line? Because you're looking on top of the plate, so you can see this plate edge, but this is like the plate edge underneath that like would be there if you had X-ray vision. Does that make sense? That's a good question. That's a really good question. And so this further illustrates that these are literally the exact same plates just lapped onto one another, right? It's like I fabricated 2 identical plates and connected them with A325 7/8 inch diameter bolts. With me so far? All right, let's get to work. Okay, so we have 2 limit states to assess. The first is bolt shear. Let's do that one first. Okay, so let me move this out of the way. All right, so let's look at bolt shear. Okay, so bolt shear. What were the bolt diameters? We have A325. What does the spec refer to that as? Group A. What would be Group B? There we go. All right. So what about the threads? Are they included or excluded? So how do we refer to that? We say group A what? X. And then here's a big question. Are we in single shear or are we in double shear? Single shear. That's 100% right. So with all of this lovely information, we can go to table 7-1 on page 7-22, and we can determine the capacity of a single bolt. So what is the capacity of a single bolt with these conditions? Say it again. 30.7. And what I like to do is I like to use a little r for my connectors. So like what I will do is phi little rn is kips per bolt, or I'll say phi little rn is so many kips per inch of weld. We'll do that later when we look at welds. All right, so each bolt can withstand 30.7 kips per bolt. I want to make sure everybody else was able to find that in their AISA 15th edition steel construction manual. Is there, any questions?
I'm guessing the higher one's just like a range too, so
Well,
use the lower for.
no, hold on.
Oh yeah, okay, I remember.
Yeah, remember that. Yeah, that's single shear versus double shear. So it's double because there's two planes.
Okay.
So if, for instance, you ever had a bolt that was in triple shear, just take the first one, multiply it by 3. Yeah.
So is like double shear, would that be like 3 plates?
Yes. Yes, and that happens in splices, right? When you have a beam and you have a plate and a plate on top and you yank it, so you have 2 shear planes. That happens all the time. Yeah. Double shear conditions are very common. If you ever see a beam splice connection in a bridge, look at the flanges. The bolts are in double shear. So, any questions? Now, how many bolts are in the connection? 4. So, what that means is phi Rn is kips per bolt, 4 bolts. I might be able to do this one in my head. So 30 times 4 is 120. 7 times 4 is 28. 2.8, what is that, 122.8? So this is the capacity of the bolts in shear. So this is how much load it will take to shear those bolts in half, okay? Now, there are other limit states which may or may not govern the behavior. Gross section yielding, net section fracture, block shear rupture, etc. Right now we're just looking at bolt shear and our second limit state, which is bolt bearing, okay? So we need to look at bolt bearing. But before we move on, any questions about this? Hopefully this is simple. All right. Now, a couple things about bolt bearing. So, remind me, the bolt diameter for this problem is 7/8 of an inch, and so the hole diameter is what?
15, 16.
You add a 16th, that's 100% correct. We're looking at the physical dimensions of the hole. Does that make sense? Now, I'm going to draw the plate here because I don't want, like, the formulas are really simple. I just want to make sure that we all kind of understand the physics of what we're talking about here. So we have a hole, 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 hole. This dimension, 3 inches, 2 inches. Is that right? So what we've got here is a situation where S is 3 inches, LE is 2 inches. That's the only time you'll ever see me write cursive. And I'm very tempted to just use a big L because, yeah, cursive. Nah, not a cursive fan. Anybody a cursive fan?
I wasn't even taught it.
Really?
Yeah.
That was like 2nd grade was cursive for me.
Are they always going to be 3 inches, like left and right, and 3 inches up and down? Or are they going to have different?
No, that's a great question. That's a great question. Not necessarily. Typically, what is done is if we're talking about spacing this way, however many lines of bolts there are, they're usually either evenly spaced or grouped, like together. But like for example, but that's not always the case. Like for example, if you have a wide flange and you have bolts through the flange, then they're not like 3 inches apart. They're like middle and middle, whatever makes sense from a fabrication perspective. Does that?
Yeah, so S is parallel to the flange.
Okay. From a capacity perspective, yes, right? Because if we're yanking on the plate this way, what we're interested in is either the bolt bearing failure with the plastification, or we're interested in that like region tearing out. Make sense? So what we need from this S and LE value are this and that. So LCE and LCI. Now, here's another point that's worth making. The bolt spacing requirements that we're going to check here in a little bit about bolt spacing and edge distance requirements, the ones that don't have anything to do with strength, the ones that have to do with whether or not the connection can be put together. We also need to check this one for that, because this dimension doesn't have a hill of beans to do with strength, but it better not be 1/4 of an inch, otherwise we still can't put it together. Right? Does that make sense? But from a capacity perspective, that's all we care about. Does that make sense? All right. So LCE is that. And anybody, oh my goodness. Anybody got an answer for me on this one with your Casio FX115 ES Plus or similar scientific calculator that I know everybody brought with them on this dreary Friday, soon to be afternoon? What'd you say? Something like that? Okay, so LCI is that. So is everybody okay with these formulas? Do you get why they work, right? So LCE is the edge distance minus half a hole diameter, and then LCI, we take half a hole diameter, so it's S minus DH. Is that, everybody okay with that? Okay, all right. Let me know if you're not. That's okay. All right, so this is, I can do this one. It's 2 1/16, or 2 and 2.063 inches. Okay? Now, we have all the values. Let me show you how I do bolt bearing, because I like doing bolt bearing calculations with as few repetitive computations as possible. Like that's how I like to do it. So let me show you how I do it. Okay? Now, the expression for bolt bearing is the minimum this is the expression, which, by the way, what is FU? And that was from table 2-4 for A36 steel. Okay? This is how I like to do it. Okay? So I like to do some intermediate calcs first. So I'm going to do 1.2 LCE TFU. Was this a 1/2 inch thick plate? Yes, it was. And so what do we get for this? We'll say to 1 decimal place. This is good enough. Second? Okay. Now what I'm going to do is the same calculation but with LCI. So all I did was replace the LCE with LCI. So you could probably just take whatever in your calculator, divide it by this, and multiply it by that. 71.8. Do I have a second on that? Okay, and then lastly, this one. So remember, these two are very mechanics based. They're like mini block shear checks, because you're doing like this path in shear and this path in shear. So it's like 2 times 0.6 times the area in shear times FU. This one's empirical. This is just when that hole starts to plastify. It starts to mash up, and yield. 60.9. Okay, do I have a second on that? Okay. What?
For some reason, his 60.9 didn't comprehend 60 in my head.
I was saying that because I didn't know 60 or 16. So, is that right?
Yeah.
Okay. All right. Okay. With me so far? The reason why I like to do the intermediate calcs is this, is because I like to say, so here's the thing. If you want the nominal capacity of an edge bolt, it's the minimum of this. And what is that? So an edge bolt is the minimum of bolt tear out or bolt a hole ovalization. And so which is that? 53.3. So we already did the math. We don't need to do it again. That's kind of, I like to do this because it's the minimum number of button crunching you have to do in the calculator or the calculations. And RNI is the minimum is this. So it's the minimum of this and this. And so which one's that? 60.9. So behaviorally, what is this saying is going to happen under the limit state of bolt bearing? It's saying that the edge bolts are going to want to tear out, but the interior bolts are going to want to plastify, right? Does that make sense? Which again, we're talking about ultimate limit states. This isn't that unheard of. Now, this is the capacity per edge bolt. This is the capacity per interior bolt. So what is the nominal capacity of the entire connection? Well, it's the number of edge bolts and the number of interior bolts. How many edge bolts do we have? Huh? 2. And how many interior bolts do we have? Hold on. Here's our plate, our single plate. How many of these are edge bolts and how many of these are interior bolts? Now what you're saying is that for the other plate, those interior bolts serve as edge bolts. But we're looking at it one plate at a time. 2 are interior, 2 are edge. Does that make sense? Okay, so the nominal capacity of the connection as a whole is 2 of this plus 2 of this. And so what is that? $228.4. Do I have a second on that? Is that the capacity according to bolt bearing? You're saying no. Why? No. We're talking about per limit state. What am I forgetting? Say it again. The phi value. We need a phi value of 0.75. All this is just the nominal capacity. We have to adjust it by our LRFD resistance factor. So this is 228.4 times 0.75. And what is that? This is our limit state capacity. Now, Mr. Hale, I think you were getting ahead of yourself, but you're still not, I don't think, wrong, right? What were you saying? Yeah. So unfortunately, we did all this math and it didn't matter, right? Because in the end, if I yank on this connection, what's going on? So the bolt bearing capacity is 171.3 kips, but our bolt shear capacity is 122.8. So if I take this connection and I yank on it, the bolts are going to shear at 122.8 kips before we achieve the bolt bearing capacity of 171.3 kips. So assuming that these are the only 2 limit states that we need to assess, what is the capacity of this connection? It is 122.8 kips. Now we're not done because we got to do our spacing and edge distance checks. But before I do, are there any questions? Does this make sense? Everybody okay with this? Okay. Let's look at our layout requirements. And we have S is 3 inches. That is 2 inches, which, by the way, if you look at the very beginning of the connection, remember how I said you need to check this spacing as well as this spacing? They just kind of happen to be the same, you know. It's kind of funny how I did that. 3-inch bolt spacing is actually very, very common in steel design. It's very common to use a 3-inch grid across the board because 3-inch grid tends to meet a lot of spacing limitations, and we're going to see this here in a quick second. Speaking of, what was the minimum bolt spacing? There you go. Which is 8/3 times, oh, maybe I should do this. So 8/3 or 3/4, the 3's cancel, and I get 8/4, which is 2 inches. Oh, 7/8. See, I couldn't remember. All right, so I might actually need your help on this. So 7/3 is 2.33 or 2.67. Yeah. I've never been accused of being able to do math. Now, S max is what? It's the minimum of 2 things. What are those 2 things? You remember? It's 14 times the thickness, or 7 inches. Okay? Now, what's 14 times the thickness going to be? 7 inches, so it's going to be 7 inches, yeah. Now, do we meet these limits? What is S? We meet those, right? Because our bolt spacing is between the minimum and the maximum. And usually, bolt spacings tend to hover a little closer to the minimum than we do the maximum, because that ensures a more economical geometry. Now, we have LE min and LE max. The max is computed as the minimum of 12T, or 6 inches. But again, that one's going to be pretty easy because that's just going to be 6 inches. The minimum, however, is a lookup. If I have a 7/8 inch diameter bolt, what is the minimum bolt spacing, or minimum edge distance spacing? Remember, we find that in table J3.4. I believe that's on page 16.1-132. 1 1/8. Everybody see that? And our edge distance is 2 inches, so again, we're okay. What do you think? Is this too bad? Hopefully this is simple. I mean, bolted connections and welded connections are some of the easier topics in the class. There's a little bit of math that you got to do, but it's not super rigorous. The processes aren't super involved. It's just counting and making sure you dot all your I's and cross all your T's. Are there any questions? Did I get the right? Hold on. Yeah.
Oh, okay.
Yeah. So 7/8, 1 1/8. So. And again, the reason for the tabulation is because that comes from the fabricators. So I believe that there is a table J34M as well, which I think is for metric. Is that right? Again, I don't believe in metric, but that's a joke. That's a joke. Hopefully everybody has your umbrellas, although I'm sure Dr. Waite will teach you about infiltration and all that jazz in hydrology. I will see you all on Monday. You all, what's up? I'm sure you're having a hard time containing your excitement. Just don't lose your head. I will see you all on Monday.